All right, we're going to look at problem 114 in your textbook, and I'm going to go through the solution, but the main reason for going through this is to show you how MathCad does definite integrals. And so the problem statement here, I've given you the solution, but let me just read the problem statement. It gives you a differential equation for how the fluid pressure varies with height. And so it's dp dz is equal to minus rho g, where rho is the density, g is acceleration due to gravity, and then we are going to assume an ideal gas for air. And then what we want to end up doing is basically calculating the pressure in at 1 mile up in the air versus sea level. And so they give you the example of Denver, which has an elevation of about 1 mile. And so if we're to ignore this for a while, but if we're to go through with MathCad, the first thing we do is we start listing the information that's given to us. So Z1 at sea level is equal to 0 meters. I don't like using zeros as my subscripts or O's. I like using 1s and 2s when I do definite integrals, so that's why I'm doing that. Z2 is 1609 meters. That's one mile elevation. And then the molecular weight, they use capital M. So capital M is fine for that. It's 29 grams. Remember, grams is GM. It's not G, because G is the acceleration due to gravity. Grams per mole. MathCad does have moles as units. And then my R value. This is where MathCad is really nice because I don't have to go and look up and try to choose an R value in the most convenient units possible for doing unit conversions by hand. So I just remember 8.314 joules per mole Kelvin, and MathCad can handle that, and I can go on my merry way. Atmospheric pressure at sea level is 1 atmosphere, and so MathCad, this is an example of where, even though I don't like using English units, I can use 1 atmosphere, or I can use 14.7 pounds per square psi, and MathCad can handle it. And then my temperature is 10 degrees, so that's 283 K. One thing about MathCad, at least my version of MathCad, is it does not do degrees C. I believe the MathCad 15, later versions can handle degrees C. But my version of MathCad does only absolute temperatures, which is fine because in thermodynamics, most of the time, especially when we're doing second law, everything has to be in absolute temperature units. So temperature is 283 K. And then we want to find P2. So going along with our problem-solving strategy, the assumptions we can make, number one, is that we've got constant properties. So the molecular weight of air is not changing. The ideal gas constant is not changing. The temperature, as we go from sea level to 5,280 feet or 1 mile elevation, is constant, as is the acceleration due to gravity. You could also say that we're assuming, although we're told explicitly, that we can use the ideal gas equation of state. And so using the ideal gas equation of state lets us plug in for the density in the original differential equation that you were given. So the density is just the concentration. So remember that the ideal gas equation of state is PV equals, I should say P times V is equal to N times R times T. So density is just N over volume, right? That's a molar density. So N over volume is equal to P over RT, and so that's what they substituted. That's what they substituted into this equation here. So once we get this equation, we want to solve for the pressure as a function of height. And so we can do that by integrating. And as you go through here, you see, of course, that we can't just integrate this equation. We first have to separate and then integrate. Now this is where I want to focus on MathCad integration. MathCad will not do a good job of getting you from here to here. MathCad does not do a good job of separating variables and getting this. At least my version doesn't, and I don't think yours does either. If it does, great. Go ahead and figure out how to do that. But what MathCad is good at doing is once you get an equation with a single integration term, it will do that integration very nicely for you. And the reason why I want to go through this is because when we get into chapter 4, we will be, instead of doing a very simple integration, this is just log of P2 over P1, and then the integral of dz is just delta z, right? You can do that in your head, just no problem. But when we get into chapter 4, we're going to have integrals of Cp dt. All right, we're going to have integrals of Cp dt. We're also going to have integrals of 1 over Cp dt. And those integrals are not going to be so easy to do. Now, if Cp is constant, yeah, it's easy, right? But, or not, we'll have integral, sorry, that's going to be Cp over t dt. All right, so if Cp is constant, that's an easy integral to do. This is just Cp dt, or delta t, and this is Cp times log of T2 over T1. The challenge is going to come where Cp is a function of temperature, and it's a complex polynomial function where the temperature is raised to both positive and negative values. And what I remember from being a student in energy balances or thermodynamics is whenever I was in the middle of an engineering problem and I had to do this long drawn out manual integration of a higher order polynomial that has both positive and negative exponents, it was always a royal pain. And I just hated doing those kinds of problems. I would almost, it's not right, but I would almost rather just assume a constant heat capacity and just take a 5-point hit to avoid the pain of doing those integrals. I never did that, but that's often what I thought I should do. But anyway, the nice thing is that MathCad can get rid of all that pain of doing those kinds of integrals for you, and we'll show you how to do this with this very simple step. So what I can do then is, like I said, MathCad will not do the separation for you, but it will do the integration for you. And so what we'll just give you here is the partially integrated form. So natural log is just ln in MathCad, parentheses p2 over p dot 1, close parentheses, symbolic control equal. And so now I'm going to, so I can integrate this by hand just fine, going from here. So now I'm going to do a definite integral. So I've got the integration toolbar up here permanently displayed. You can go to your menu and change that if you like. So I click on that and it gives me my definite integral. So all I have to do now is start filling in these little blanks with a cursor. So z dot 1, z dot 2. I'm integrating with respect to z, and now I put my term in here. And so this is minus capital M times g. MathCad already knows that g is acceleration due to gravity, divided by r times t. All right. And so that's my definite integral. And now, of course, as I mentioned, you can do this by hand and get the answer pretty quickly, but if this were a big multi-term polynomial expression, it'd be a real pain. So if I want to solve for P2, I just click, highlight P2, go to variable, solve, and that's my expression. So I have, oops. So then I can either cut and paste it, or I can do P.2 control or shift colon is equal to that term, and there's my answer in pascals. So MathCad is very good at doing these definite integrals for you. And if I wanted these in different units, I could put it in PSI, I could put it in atmospheres, I could put it in newtons, pascals, so on and so forth. So that's how MathCad does integration. And like I said, you will be glad to use this when we get into chapter 4, 5, yeah, especially chapters 4 and 5 and 6, where we have to do a lot of problems where we cannot assume that the heat capacity is constant. We're going to have to integrate Cp dt or Cp over T dt.